Section 6.4, modeling data with a curve of best fit. So now we're talking about curves. So we're going to look at quadratic or cubic functions that best fit a set of data. So look at this here roller coaster. And what we want to know is the characteristics of the polynomial function that might be used. So we're really calling on that information we learned in section 6.1 and 6.2. So if this were on a Cartesian plane, just imagine anywhere, we would see that it would start in quadrant 2 and end in quadrant 4. So that it also has one turning point, two turning points. So that's going to tell us that this is probably a cubic, and because where it starts and ends, it's probably a positive cubic. So if we have data that looks like that, we might be able to model it with some sort of equation that looks something like y equals x cubed. So that's basically what we're going to do. So here we have Audrey. She's interested in how speed plays a role in car accidents. She knows that there's a relationship between the speed of the car and the distance it needs to stop. She has found the following experimental data on a reputable website, and she would like to write the summary for a graduation class website. Okay, so those of you in physics, and I talk about physics because I'm a physics teacher as well, speed and distance needed to stop. So when you stop, that's negative acceleration. And if you know anything about acceleration, you might already have a clue about the relationship between speed and distance. You might see that relationship. Okay, so we have all this data, a whole bunch of data. We're going to plot it on a scatter plot. So what I'm going to use once again is Excel. So I've entered in all that data. And sometimes these questions entering the data is going to take a lot of time. I'm going to highlight the data that I want. And just like with linear regression and linear modeling, I go to Insert and I'm going to create a scatter plot. So this is what my information looks like. So now we have to do the job where we have to say, okay, if this were on a Cartesian plane, what does this look like? And you could say a line, but it kind of looks a little more like it's curving. It almost looks like, whoops, half of a parabola. I lost it. Where did I go? Oh, I went too far down. There we go. Kind of like half of a parabola. So we're going to see if we can model this with a parabola. And we're just like last time before, we're going to go to layout and trendline, but we're not talking about linear. We're going to go to more trendline options. And we're going to do polynomial. Order 2 means we're looking for things that are quadratic. That would be cubic, etc. Okay, so we want quadratic. And again, I'm going to display that equation on the chart. Okay, and here I have my very beautiful curve of best fit. So Excel has done most of the work for me. That is my curve of best fit. Okay, now what the question asks. Let's see what this question asks. Sorry, I'm flipping. So it says, use your equation to compare the stopping distance at 30 kilometers an hour with the stopping distance at 50 kilometers an hour to the nearest tenth of a meter. Okay. So 30 and 50 aren't exactly on here. Well, there's close to 50. Sorry, no, but we're doing 30 kilometers an hour. I don't see 30 kilometers and 50 kilometers an hour on here. So it's not something we can just take. What we're going to have to do is we're going to have to sub in to our equation. Okay, so remember our equation was right here. It was y equals 0.0083 x squared. That's our equation. And what I'm going to do is I am going to use this equation and sub in the values of 30 kilometers. So when x equals 30 kilometers an hour. And I'm going to sub it into my equation. Remember, my equation was y equals 0.008 x squared plus 0.0539x minus 10.449. Okay, so I'm subbing in everywhere where I see x. I am putting in 30. Okay, doing some calculator work. If I had a good calculator, I could put this all in using brackets and it would spit out the value. My y would be 13.203. So, and remember my x is my speed, my y is my distance, so that would be that many kilometers. Okay, now it also says I'm supposed to compare this at 50 kilometers an hour. Stopping distance at 30 with 50. Okay, So I am going to sub in the value of 50. Again, if I have a good calculator and I use my brackets, I can put that in my calculator all in one shot, and I would get 37.256. Just a second. This gives my distance in meters. Sorry, the relationship gave meters, and I wrote kilometers. I made a mistake. This should have been just meters. Okay, so I got 37 meters. So if I compare, it looks like it is about 3 times as big. 13 times 3 is roughly 37. The next part of the question says, determine the maximum speed the car should be traveling in order to stop within 4 meters, the average length of a car. So if I want to stop within 4 meters. So what I'm going to do is I'm going to put 4 in for y, and then I'm going to solve this equation. 0.008 x squared plus 0.39x minus 10.449. Okay, so here I have a quadratic equation. It doesn't look like this that I can factor. So there's a couple things that I could do here. I could solve by graphing, or I could solve by the quadratic equation. And I think what I'm going to do is I am going to do solving this by graphing. So I need the internet. And I do Desmos graphing calculator. Some of you have graphing calculators like a TI-83. That would work as well. So what I'm going to do is I'm just going to bring the 4 over. I'm going to subtract 4 from both sides. So I get 0. And then I'm going to be looking for the x-intercept. So 0.008 x squared plus 0.539x. I've subtracted 4, so this becomes 14. Okay, so now I'm going to go to my graph. I'm going to say y equals 0.008 x squared plus, honestly, entering this stuff in is going to take the most amount of time. 39x minus 14.449. So let's see what that looks like. It looks like I'm going to have to do some zooming. Zoom, zoom, zoom. There we go. The model is only looking at this part right here, so I need to know that intersection right there, and it looks like it's 20.54. So again, back to our question, it says, determine the maximum speed that a car should be traveling in order to stop within 4 meters. Well, it can only be going 20 point, what did we say, 59? I have an awful, 0.54 kilometers an hour. Okay. Let's look at another example here. Okay, the following table shows the average retail price of gasoline per liter for a selection of years in the 30-year period beginning in 1979. So someone has found this data. So in 1979, it was $21.98. 29 years later, it was 115 cents. This is really sad. Here's when I started driving, I remember it was around 54.9, around that. But you know what? I started driving more than that many years. So maybe I was just in a good part of the country when I was driving. Anyways, gas prices make me sad. I don't know if they make you sad too. Okay, that's not what I wanted to do. Here is the data. So I've entered in all this data, and I am going to make a scatter plot. So I go to Insert, Scatter, and here I have my information. So when we look at this and we looking at polynomial functions, if we imagine this is on an xy, I would see that this starts in quadrant 3 and goes to quadrant 1. So I'm thinking it's probably going to be cubic. So when I go to my layout and I add a trend line, what I'm going to do is I'm going to go to polynomial, but instead of order 3, I'm going to make it cubic because I'm pretty sure that this one is going to be cubic, and I'm going to display my equation on the chart. And that looks pretty good. So just to show you guys something, if I made a mistake and I said, no, I really want this to be quadratic, it's still, whoops, I've lost it. It would still make a graph of best fit, but you can see that's not as good as the one that I have made. So, I mean, you can make a mistake, but your intuition should tell you it doesn't look that good. Okay, and there's my equation right there. So look, it is indeed a cubic. It has a positive coefficient. That makes sense because it starts in quadrant 3 and goes to quadrant 1. So, oh, I'm scroll happy today. There we go. There is our equation. So looking at that equation, there's a couple questions that we need to look at. What does the slope and y-intercept of the linear regression represent in this context? Oops, that was the wrong question. I wrote the wrong stuff here. Let me fix that. Sorry about that. So what does the constant term represent? So let's look at our graph, and the constant term is 23.452. Well, if you notice, that's really close to the point 0. And this is, again, a estimation, but it does represent the price at time 0 or year 0. It's close to that. Okay? Next, it says use your equation to estimate the average price of gas in 1984 and in 1985. So what we do is we take that equation that we got from Excel, which was, oops, I'm going to do the same thing. We had y equals 0.0123x cubed minus 0.4645x squared plus 6.295x plus 23.45. And what we're going to do is we're going to put in the x value of, well, we want 1984. So we're not going to do the x value of 1984. No, no, no. Instead, we are going to look back to the question for a second. It says years after 1979. Okay, so this would be 1980, 81, 82, 83, oops, 84. So that'd be 5 years after. Okay, so x equals 5. So that would be a common mistake, just reading that wrong. So subbing in, if we put a 5 in every time we see that, so we cube it here, square it, we would get 44.9 cents per liter. We're going to do the same thing with 1985, so that would be x equals 6. Plugging it all in, we would get 47.2 cents per liter. Okay, so just plugging it. Now, the next question says, estimate the year when the average price was 56 cents per liter. So now my y equals 56, and I'm solving 56.0, and I'm solving for x. Okay, so what I'm going to have to do here is I'm going to have to graph again, because I don't really have many tools to solve a cubic. So we have 56 equals 0.0123 n cubed minus 0.4. Okay, I'm just going to pause and get that already on the graphing calculator. Okay, so I took a little different route to solve this one. I wanted to know where, since our equation was 56 equals this cubic, what I did is I said, first I drew y equals 56 and got a constant line. And then I did that cubic, and I want to know their intersection. And I can see their intersection is at 16.4. That's where the x value, where these two functions equal. So what I'm going to do is I'm going to take that 16.4, and I have to add that to 1979 because it's 16.4 years after, and I get 1995.4. So the average, in 1995, the average price was 56 liters. And I rounded down because it's 0.4. You could also say in the middle of 1995 or in the first 3 months, because that would be a quarter of the year of 1995. The average price was 56. Okay, so just some summaries here. If there's a predictable curve, there could be a quadratic or cubic. Graphing technology is what we're going to use. And to solve an equation, you can graph the function of each side of the equation. The x-coordinate of the point of intersection, that's what we found. The x-coordinate is the solution. So either you can graph both sides, or I could have brought the 56 over and then done with the x-intercept, either one. Technology uses regression to determine the curve of best fit. It results in an equation and a curve that balances the points on both sides of the curve. A curve of best fit can be used to predict values that are not recorded, and that's what we did. Predictions can be made by reading values from the curve or by using the equation.